Um, Thank you very much for being here despite being late in the day. So I'm Bobby Prévost. I'm a research scientist at 3GDNI based in Montreal here in Canada. The motivation for our work was to take into consideration the small retailers that often have a high inventory rate in their products. So for such a retailer, it will be pretty difficult to gather a large amount of data that will be significant to produce a good recommender system. And by the nature of the large inventory rotation, the database will always suffer for persistent sparsity, which is due to the constant amount of product that goes out of stock and that create a transaction unusable for the recommender. And that will also create a recurrent cold start problem. So the approach in this paper was to elaborate a technique that will help to minimize the amount of unusable transaction, but also provide a popularity bias control and be able to be updated real time. So for that work, we use a privately provided data set that contains a slightly less than 5,000 products, but which of them only 400 are in stock. And this is spread out among less than 6,000 users. And from the 100,000 transactions, we have 69,000 of them that are conducted with product out of stock, which means this is efficiently not useful for the recommender. And just looking at the distribution of the sales, we see that as expected, most of the users have very few interaction with the stores. So to mitigate the sparsity problem, we came up with what we called a time Scintillation mapping that literally will map the out-of-stock item into the item that are currently in stock. So in order to do that, we had access to all the images from the product in the database, including the historic product, obviously. So what we did is that we encoded all the images of every product using an ensemble of CNNs. They were pre-trained on ImageNet with the softmax layer removed, so we could extract only the feature vector. Using the feature vector, we calculated the distance between the images using a nearest neighbor algorithm, and then we could simply associate all the out-of-stock product with the closest in-stock item within the same category of product, of course. So by doing so, we were able to, first we had to set a certain threshold of distance to make sure all the products were still similar enough. So with that threshold, we were able to convert about 91% of the transaction conducted with the out-of-stock item to items that are currently in stock. And the sparsity of the matrix, not the sparsity, but the occupancy of the matrix went from 0.6% to 5.5%, which is much more manageable for a recommender system. And due to the nature of that technique, the occupancy is only bound to increase over time. But that technique led to an obvious problem of bias in our system, so in the database. So when we look at the transaction, the popularity of this transaction, we artificially boost products that were already popular or have a more general look. So to mitigate that problem, we simply came up with the idea to look for the next nearest neighbor. So we just set another parameter, sigma d, that just allows us to look at products that are close enough to the first neighbor, but in that case, we will select always the product that is least popular. So in that case, we were able to significantly reduce the popularity bias. And that is pretty important because if we're not doing that, that will obviously bias the recommender and we'll always end up with the same recommendation and the system will always think it's right to do that. So having all the product, the images, the distance, we can now build our complete data set, training data set. So for that, we went through the user history and extract all the pairs of items that were bought together within a fixed delta t. So we decided to use an item-item framework because, as I said, the level of interaction of the user was quite low with the store. So it made more sense to try to find the complementary products. Additionally, to train the model, we obviously need to generate a large number of negatively labeled pairs. So otherwise, we would only model the popularity and not truly the correlation in the system. So that's why we had to sample these among the popularity distribution and not just the uniform distribution. For this work, we decided to work with an algorithm developed by Google that was published 2 years ago in that conference. It's called the wide and deep model. This is quite an interesting model because it fits perfectly the idea of item-item correlation. So you have on one side, you have a linear part that literally models a co-occurrence baseline, and the wide part is able to learn the additional correlation, including also the effects of side features. So, I mean, with that, now that we have the training data set, I mean, we just train it, and to get the probabilities, we just sum for each user over the purchase history. And while knowing the information regarding the distance, we can also came up with a lot of custom business rule that the client will need, and that could be based on item similarities, like the concept of likes or dislike, where you can up-rank or down-rank certain items based on the distance in the feature space. So all in all, I mean, that came up with a complete model where offline you can encode all your images, you calculate the distance, train the model, and then store all the prediction. And online, all you have to do is to update the prediction based on the user session, and then you query the user probabilities online that you just sum to get the recommendations. So in terms of experiments and results, we characterize the system with the AUC and the coverage. In our case, the coverage is an item will be defined as covered if it's recommended to at least one user within the top 8 recommendation. That is purely based on a business rule imposed by the website. So for that, I mean, yeah, of course, we use the deep learning model, but also built a simple co-occurrence metric to serve as a baseline. And the point was not to compare the both model, but to show that the time translation mapping led to an increase of AUC in both cases. In case of the co-occurrence metrics, it went up by at least almost 10%. And with the deep learning model, it went up for about 5%. And this is only due to the decreased sparsity in the metrics. But what's important to see is that that decreased sparsity preserved the integrity of the correlation in our data sets. And well, additionally, if we take into account the next nearest neighbor, that's interesting to see that it significantly increased the coverage that we had with only the time translation, but it also preserved the accuracy. So in that case, we did not add the trade-off of the of coverage versus accuracy, which is a recurrent problem in most database, well, in most recommender system. And actually, the AUC slightly increased with the NextNearest Neighbor in both model, which is most likely due to a more uniformly filled matrix where the system, the model could more easily find the proper recommendation. And if we look at that, the distribution, the popularity of each item in terms of recommendation, we see that the use of the NextNearest Neighbor really moved the curve to the right and significantly increase the amount of recommendation, not only random recommendation of 1 or 2 times, but they're systematically recommend to a lot of user too. So, well, in conclusion, yeah, we built a time translation scheme that will, that maps the item out of stock in stock based on image similarities, which increase the accuracy. And also we provide, we extend that model to that system to provide a bias control that would increase the coverage at no accuracy cost. And that's interesting also to take to think about the cold start problem in that case, because that in a way that was not necessarily the goal of the system, but in the end it provides a solution to that, because every new item added into the system are bound over time to be similar to an older product that is out of stock. So as soon as a new product enters the data set, it gets immediately associated with transactions which are, as we saw, is still relevant to the correlation of the model. So in terms of future work, I mean, obviously that was a short paper, so we did not add the space to elaborate many more metrics. So we have liked to, of course, explore more the top K accuracy to get a real sense of how it improved the quality of the recommendation itself, not just the AUC. And also it will be interesting to move that technique to other type of deep feature, because the work was focused on images, but it is not limited to that. So any kind of feature that you have associated with a product where you can extract, well, feature, you can still correlate that and use your the distance to find that. So that could be used like item description with a word-to-vec model, or anything that will came up in our data sets. So, well, thank you very much for your attention. Any questions?
So we have another very clear presentation, it seems.
Apparently. No.
Okay, so thank you very much.
Thank you.
Once again.